In this session, I'm going to talk about classification regions. What is a classifier? What is a classification region? And some examples. On this diagram, you got a typical classifier. So you got features, datasets, class labels. So remember what we've seen last time in the session about data and datasets. Features were x1, x2, x3. Remember the spreadsheet? That's the columns. Class labels, omega 1, omega 2, etc., etc. So basically, we got something in the middle that we call a classifier, a routine, an algorithm, whatever. And that's going to look at the features from objects in a dataset in order to predict class labels. So there are three main steps. One is training. So is to try to figure out to distinguish between the different classes. Then a phase of test, and once it's all working well, as well, that's the expectation that it's all working well, then you can deploy it. So let's have a look at this example. So first of all, a classifier is any function, method, or algorithm that assigns a class label to any given object. In this example, we got two classes, the points in black and the points in red. And we want somehow to be able to distinguish between the two and predict for any new point if it's class black or class red. So we got this new data point. Should it be red or black? That's the question. Well, I would probably assign the class red. So here I just draw a line, so it's a linear classifier, and it splits the dataset in two parts, the black part and the red part. And as you can see, there might be some errors like here and here. Class black, class red. The classification regions may consist of disjoint parts, and they may be of any shape. So here you can see the shape. It's no longer like a line, and you got two areas that's quite clearly separated. And here on the right hand side, you can see that this is disjoint, like the region of the red class is, well, you got two subregions. Notice the connection. So the classifier is going to produce a classification region. So one determines the other. So this one on the right hand side, it's called a piecewise linear classifier. So let's have a look at this one and try to find the classification regions, meaning find a classifier, because if you can find the region, then it's that you found the classifier that finds the regions. Here we got three classes, the yellow triangles, the blue circles, and the green squares. We got two features, x1 and x2. And capital N, there are 900 objects. So we can separate the green class from the other two classes. So that's one region. And here it's all two other regions. It seems pretty trivial in 2D. We could add more dimensions, more features. And here, because we are separating the space using lines, well, we have linear classifiers. So we got three regions: the green region, the yellow region, and the blue region. Well, let's try to define an algorithm that will be our classifier. So if x2 is less than 3.5, then the class is green. Else, so we are above. If x1 is less than 1.5, this is class yellow. Else, meaning it's above, this is class blue. So you see that a classifier does not have to be something very complex. So this is a rule-based classifier. So these are rules. And we got our 3 classification regions. So now we got one feature, x1, and we want to find a classifier. So, well, we could have just a split like somewhere here maybe, and anything on the left is class black, anything on the right is class red. Or we could have a piecewise classifier. So this is black, this is red, this is black, this is red, and this is black. Careful here, is it a bit of noise? Should it be red? We don't have enough data to know. So one rule of thumb, the more data you got, the better. Now we're going to look at the notion of discriminant functions, and we started to see that a little bit in the lab. So what is a discriminant function? How do we calculate a linear discriminant function in 2D? And the canonical model of a classifier. So back to our example. We want to design this classifier. So we pick up 2 points, A and B, on the line. We must find the line equation. And here, this is one way to find the line equation, which is here. I can show you a different way of doing it actually. So I'll do that from here. So you know that x equals ax plus b. So now we pick up, we know actually what a is. So a is equal to the change along the y-axis divided by change along the x-axis. Oh, that's not very pretty. Let me do that. That's better. So looking at our line, so change in y. Well, it's going down by 1, 2, 3, 4, 5. I mean, this is 0 minus 5. So minus 5. Change in x. This is 5 minus 1. This is 4. So this is the value of a. So y is equal to this times x plus b. I have to change the font. I'll make it a bit smaller. Right. Let's consider point A. So 5 is equal to this times 1 plus b. So basically what we don't know is the value of b. Well, b is equal to 5 minus this. you notice that you got minus minus, so we could get rid of the minus. So b is equal to this. So if we multiply now this number by 4, so what I want to do is to get rid of the 4 here. So this is times 4 divided by 4. So we got this. So 5 times 4, this is 20. 20 plus 5, this is 25. So 25. So this is the value of b. Now we have the equation. So y is equal to ax plus this. We could try to get rid of the 4. So if I multiply this by 4, so now we can get rid of, oh, I forgot to multiply this one by 4 here. So that means that we can get rid of the 4 here, the 4 here, and the 4 here. And now, if you look at this, I'm going to pass that on the other side. And this is our line equation. Same as here. It's just a different way of doing it. So you know the equation of a line. Y is equal to ax plus b. A is the change along the y-axis divided by the change along the x-axis. So we can get that from the 2 points. Then we replace a by its value here. We replace y and x by their values for one of the points. I have to pick up a in that case. We figure out the value of b, and then we got our line equation. So this is our discriminant function. So that's how we write it here. But you know, this is basically the same because x is our features here. So we write it as a vector. So class red is for negative values of the discriminant function. Class black is for the positive values. So we got two classes. One, so you assign a class based on the sign in that case. So let's have a look at this point. Q. So I'm going to use a calculator. So back to the slide. I want my calculator. So I'm going to use a line equation here. So minus 5 times 4.5 minus 4 times 3 plus 25. This is negative, and as I said previously, if the sign of the discriminant function is negative, then the class is red. So this is a red point. So same again here for 1, 1. Replace the value of x and y in the equation here, x1, x2. The value is 16. This is positive, so this is class black. What could we do in that case when we only have one feature? Well, we look at the, we want to know if it's positive or negative. So if it's negative, this is red. If this is positive, this is black. So our discriminant function in that case is 0.88 minus x1. So if x1 is, let's say, 1.2, like here, 0.88 minus 1.2 is negative, so this is class red. For this point, minus 0.2, so 0.88 minus 0.2, this is a positive number, so this is class black. And this point 0, well, that'll be positive, so this is class black. So a discriminant function takes the feature values for an object and outputs a value that is used to determine the class label of the object. And here is a model of a canonical classifier. So you have X features and C classes, and the class label we assign to X, so capital X is, I mean, in bold characters here is an object, is the tag of the largest discriminant function. So this is something we started to do in the lab, if you remember. So if we want to rewrite our single discriminant function into two discriminant functions to conform with this model, so the canonical model of the classifier, we need a second discriminant function, and in that case this is just 0. So if we have a negative number, this is red. So G1, so if you have this point, that point produces a negative value. So this function G1 will be smaller than G2. So this is our class red. So now let's have a look at a real case scenario. So have you heard of wearable devices? So in that case, they put a device on a t-shirt, so you just stick it. And that's going to look at the motion, so the lateral motion and the frontal motion. So basically, if you move this way or this way. So 4 different positions: sitting on a bed, sitting on a chair, lying, and ambulating. And we got 2 features, so acceleration in the lateral axis, acceleration for the frontal axis. And well, if we look at the data, we can see that we can differentiate among the positions. Maybe not all of them. Like, I believe it's quite hard to differentiate between the black triangles and the green triangles. But we can definitely differentiate between the black triangle and the blue circles and the red squares. And we could pretty much differentiate between the blue circles and the red squares. So some exercises for you. Draw the class boundaries and shade classification region of classifier D given by the following discriminant functions. So you will have to go back to something like this. You have two features, x1 and x2, and draw the linear classifier. So that separates the two regions. And which one is the positive one, which one is the negative one. So try to draw the classification regions for that classifier. Another question, well, draw the class boundaries and shade classification regions of classifier D given by the following discriminant function. Here, we only have one feature, but one class positive, class 2 for negative. So two classes, one feature. So here, two features, two classes. Here, one feature, two classes. Not all classifiers are represented through discriminant functions. Remember the rule-based classifier? Well, question 3 is about this type of classifier. So same question, but with that classifier. Draw the boundaries, the shade of the classification regions for that classifier. So two classes, two features, x and y. Find the discriminant function of a linear classifier for this figure. So basically, draw a line, pick up 2 points, figure out the line equation, and turn it into a discriminant function. And that's it for now. So have a